Hello everyone, welcome. What we are going to do today is, see, we have already discussed what is direct stiffness matrix, direct stiffness method, and the concept behind it, and general procedure of direct stiffness method for truss, beams, and frame problems. Now. Then today and next two classes will give a demonstration of the direct stiffness method to different problems. One problem that we are going to take today is truss problem, and then next week beam, and then next week a frame problem. Okay. Now, so today is a direct application of the direct stiffness matrix, direct stiffness method. Please correct it. Okay, this is. Though it is not in some way it is not wrong, because it is a matrix method. It is a matrix method of structural analysis only. So, this is direct stiffness method. Okay. Now, let us start with let us take this example. And if you remember, this example we have already taken while analyzing truss. Okay. Now, all the calculations that we are going to do today is manual calculation, and this is the reason why I took a problem where the total degrees of freedom are less. But as I say, this method is a general and is suitable for computer implementation. So, if you have the larger structures, we have many members and the space frame, then the concept can be applied, the same concept can be applied, but that you have to do with the use of computers. Okay. Now, manual calculations will be difficult in those cases. Great. So, let us take this example. We have already what we need to determine the joint displacements and internal forces. We already determine the joint displacement, not joint displacement, we already determine the internal forces. If you go back to the lecture classes where we discussed different methods for analysis of truss, and this is the result for this. Okay. So, this means this point is in this is under compression. That is what our sign convention. This is under compression, this is under compression, and this beam, this member is under tension. These are the values given. Okay. Now, we will see whether we are going to get this value or not, and how easily we are going to get this value. Great. Now, so take this is the frame. You take the structure itself, remove it from the supports, and suppose this member is 1, member 2, member 3, and the joint number is 1, 2, and 3. Now, here one thing, please note that I said in previous classes as well. How you give the joint number, that is also a trick, because at the end you need to solve a system of equations, right. Now, if in a large, at the end you have an equation like Ax is equal to B, when A is a Kx is equal to say F, where K is a stiffness matrix, X is the unknown displacement field, and then F is the force vector. Okay. Now, for small matrix you can directly invert it, but for a larger matrix, then direct inversion of the matrix is not a good idea to solve this equation. There are many methods to solve these equations. And I am sure that in the first year engineering maths course you have learned some of those methods. Now, your computation become easier if you store the form of the matrix that you have. Most of the elements in this matrix will be 0. Some of the elements which are non-zero, but how these non-zero elements in the matrix are distributed in the matrix, depending on that your computation depends on that as well. So, always we want a matrix to be banded, so that your computation becomes less, your computational effort becomes less. So therefore, in order to get those banded matrix, you have to number the node in such a way that it leads to a banded matrix. So, but for this case I have given the node number arbitrarily, not really arbitrarily, I will tell you why I had given 1, 2, 3 like this. But when you actually implement this method in computer, please note that numbering of this node is also not arbitrary. You need to optimize to get the most optimized form of stiffness matrix, you need to number them accordingly. Okay. Now, for the time being you do not have to bother right now. Okay. Now, what we are interested now in to understand the concept, to demonstrate the concept. Okay. Now, so this is the member number and node number we have. Then what we have is now next is, suppose you see at every joints we have 2 degrees of freedom, right. The every joint can move in x direction and can move in y direction, and all the degrees of freedom you have to number. Now, suppose the first degree is this is 1, this is 2. So, whenever I say d1, it means that it is the horizontal displacement of node 1, d2 is vertical displacement of node 2. Similarly, d3 will be the horizontal displacement of node 2, and 4 will be the d4 will be the vertical displacement of node 4, and similarly this is the 5th degree of freedom, it is the 6th degree of freedom. Okay. Now, or the unknown joint displacement. Okay. Now, the total we have 6 joint displacement. Okay. Now, the next thing is, as we discussed, next thing is we have to break the structure into pieces and get the stiffness matrix for each small substructure, and then finally assemble them to get the global stiffness matrix of the entire structure. So, let us now, we have 3 members here. So, let us break them, let us separate all these 3 members. So, this is member number 1. Member number 1, the joint is, the point is 3 and 1, it is connected between joint 3 and 1, and these are the corresponding joint translation we have. Similarly, this is member number 2, it is between 3 and again please correct it, this is not 3, this is 2, this will be 2, this will be 2, and then we have joint number 3, member number 3, which is connected between 3 and 2. Okay. So, what we need to find out now is, we need to find out element stiffness matrix for this element stiffness matrix for member 1, which will be K1, and then member 2 which will be K2, and then member 3 which will be K3. These are all element stiffness matrices, okay, or member stiffness matrices rather. Okay. And then we need to assemble then K1, K2 and K3 to get the global stiffness matrix. So, K1, K2, K3 are the stiffness matrices for member 1, member 2 and member 3 when they are separated. Okay. Now, let us see what, if you recall, then this is the coordinate system we take, x is equal to x in this direction, y is equal to this direction, and origin we have taken, the node number 3 is taken as the origin. No, this node number 3 is taken as the origin. So, therefore, the coordinate of node number 3 is 0 0 0 0, and then coordinate of node number 2 will be L 0, because these all the lengths are L, these lengths are L, this is equilateral triangle, and then coordinate of point 1, joint 1 will be L by 2 root 3 L by 2. Okay. Now, next if you recall that for truss element, if we take a member M which is connected between ith and jth point, and the corresponding joint displacement at the ith point is I1, I2 and J1 and J2, then the element stiffness matrix, or the member stiffness matrix for this is A by L, L is the length of the member, A is the axial rigidity. The member it has only the deformation takes place axially. So, it is axial rigidity. Again we discuss why it is called axial rigidity, because if A is more, then the stiffness is more, the deformation will be less. For the extreme case when A becomes infinite, just imagine, then your stiffness becomes infinite. So, there will be no deformation at all. The structure, the member behaves in a rigid way. So, that is why it is called rigidity. Now, and then this is the stiffness. This is the stiffness matrix, and this is a symmetric stiffness matrix, positive definite stiffness matrix. Okay. And lambda x is essentially the angle that the member makes with x axis, and the lambda y is the angle that the member makes with the y axis. And if you write it in terms of coordinate, this become this. So, if you substitute for different member, if you substitute lambda x and lambda y into this expression, we get the stiffness matrix. Okay, let us do that. Now, we know that just now we have already okay. Now, let us do that. These are the three members, and these are the corresponding joints, and to consider for this case, the cross section area, Young's modulus and length are same for all members. Then what we can do is say member number 1, member number 2. Member number 1 is connected between 3 and 1. So, I will be 3 and j will be 1. This is very important, because you see, you could have taken member number 1 connected between 1 and 3, means I is 1 and 3 is 1, and if you are free to do that, but if you do that, be consistent with your rest of the calculation. Okay. Now, again the member number 2 is connected between 2 and 1. So, your numbering is, in this case your numbering is in this direction, in this direction. In this case your numbering is in this direction, and then finally member number 3 is connected between 2 connected between 3 and 2. So, in this case your numbering between this direction. So, for member 1 these become I, this is j. For member 2 this is I, this is j, and for member 3 this is I and this is j, and we will be consistent with this notation throughout the calculation. And then you substitute xi, xj, we get lambda x is for different members this, and lambda y for different members are this. Okay. Now, let us compute the. Now, once you do that, then next what you need to do is we need to substitute this lambda into this expression, and if we get for different members we have different lambda x and lambda y, and then we get the element stiffness, the member stiffness matrix for different members, and these matrices will be this. Now, you see, this numbering is important here. Now, you remember it was our truss was like this. Okay, truss was like this, and our the degrees of this was 1, this was 2, and this was 3, this was 4, and again this was 5, and this was 6, and this is member number 1, member number 2, and member number 3. Okay. Member number 1, member number 2, and member number 3. And in member number 1 we went in this direction numbering, and this direction, and in this direction. So, member number, now then the stiffness matrix for point number stiffness matrix for point number 1 will be, then what are the degrees of freedom we have? 5, 6, and 1 and 2. Okay. And corresponding element will be this will be 5, this will be 6, this will be 1, and this will be t. The first column corresponds to 5, second column 6, because this is I, this is for node I, and this is for node j. Since for this member we are going in this direction, node I becomes, node I is this point is the node I, and this point is the node j. So, first two column will be the degrees of freedom at node I, and the second will be degrees of freedom at node j. So, so node I degrees of freedom are 5 and 6, at node j 1 and 2. So, that is why it is 5, 6, 1, 2, and similarly this is 5, 6, 1, 2. Okay. Now, for member number 2, we went in this direction. So, we have 3, 4, and then 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, and member number 3 we went from this to this. So, it is 5, 6, 3, 4. So, it is 5, 6, 3, 4, 5, 6, 3, 4. This is very important, because if this is wrong, your assembled stiffness matrix will be wrong. Okay. So, be careful about it. Now, so once we have that, what we have to do is we have to assemble them. Now, for every member here stiffness matrix is 4 by 4 stiffness matrix, because every member has 2 joints and 2 degrees of freedom per joint. So, total degrees of freedom per member is 4, therefore, we have 4 by 4 stiffness matrix. Now, if you look at the actual structure stiffness matrix will be 6 by 6, because it has 6 degrees of freedom. Okay. Now, the assembling is a very important step in this process. Then how to do the assembling? Now, if you are writing a code, then also you can follow this process, the process that we are using for manual calculation as well. The first thing, we know that stiffness matrix will be 6 by 6. First, you get a stiffness matrix, initialize a stiffness matrix, which is 1, 2, these are the corresponding degrees of freedom. Okay. This is 1, 2, 3, 4, 5, 6, also write 1, 2, 3, 4, 5, 6. So, first column is for degrees of freedom 1, second for 2, and correspondingly first row is for 1, first and second for 2, and so on. And now, initialize them all, initialize them. So, this is for what? This is your 1, 2 means it is for joint number, 1, and 2, 3, 4 means it is for joint number 2, and this is for joint number 3. Similarly, this is for joint number 1, this is for joint number 2, and this is for joint number 4. So, this block is essentially joint number 1, joint number 1. This block will essentially be the how the joint number 2 and joint number 1 are related to each other, and this will be how the joint number 3 and joint number 1 is relating to each other. Similarly, this gives you joint number 2 and joint number 1, this joint number 2 with joint number 2, joint number 2 with joint number 2, this is joint number 3 with joint number 2, and this is joint number 1 with joint number 3, and so on. Okay. Now, next is we initialize all the values at 0. Okay. Initially, all the values are 0. Now, then what we do, we have 9 blocks here, right, 9 blocks here. What we do then, we will assemble, we will look at each block separately, and then substitute them. Okay. Now, let us first see block 1, block first. The block first is what? Block first we have 1, 2 here, and then 1, 2 here. So, what are the things we have here in 1, 2 and 1, 2? Here we have, this is 1, 2. This is 1, 2 versus 1, 2. This is 1, 2 versus 1, 2, and then this is also 1, 2 versus, this is 1, 2 versus 1, 2. There is no 1, 2 versus 1, 2. So, this will be this plus this. So, this block plus this block goes here. So, this will be 1 by 4 plus 1 by 4, and there is root 3 by 4 minus root 3 by 4, root 3 by 4 minus root 3 by 4, 3 by 4 plus 3 by 4, and this becomes this, you see. So, this becomes 1 by 4 plus 1 by 4 half. This is for block number 1, block number 2. Now, similarly, let us see for block number so we can see for block number, let us see, this is 1, 2 and 3, 4. 1, 2, 3, 4 means, again there is no 1, 2, 3, 4 here. In this case also, in this case this is 1, 2, this is 3, 4. So, the column is 3, 4 and row is 1, 2. Column is 3, 4, row is 1, 2, and here also there is nothing 1, 2 and 3, 4. So, these blocks goes, these blocks directly goes here. Okay. These blocks directly goes here. Similarly, it is 1, 2 and 5, 6. 1, 2 and 5, 6. Column is 5, 6. Column is 5, 6. Row is 1, 2. So, this is the block. Column is 5, 6. Row is 1, 2. Is there anything? Column is 5, 6. Row is nothing. So, this directly, this part directly this sorry, let us not. Okay. So, this part directly goes here. Okay. Now, similarly, let us see this block. This block is what? This block is 1 2 3 4 1 2, there is nothing 1 2 3 4, row is 1 2, column is 3, column is 1 2, row is 3 4. So, column is 1 2, row is 3 4, column is 1 2, row is 3 4 is this part. So, this directly goes here. Okay. And then next is column is 3 4, row is 3 4. Now, this is column is 3 4, row is 3 4, this part, and anything else? Yes, column is 3 4 and row is 3 4, this part. So, this will be this plus this. So, 1 by 4 plus 1 means it is 5 by 4, and then it becomes this. Okay. Now, then this part will be column is 5 6, row is 3 4, column is 5 6, row is 3 4, column 5 6, row 3 4, only this part. Okay. So, this part goes here, this part goes here, and this is 1 2 and 5 6, and similarly if you take from this, you will get this part is this, and then this is 3 4 and 5 6, this part is this, and corresponding this part is this. Now, you can check that, quick check, all these diagonal terms are positive. Yes, they are positive, fine, and then the matrix is symmetric. Check matrix is symmetric or not. Matrix is symmetric. Now, one exercise first you do is you try to find out the determinant of this matrix. Okay. Find out the determinant of this matrix. You find out determinant. You find out determinant of this matrix K, determinant of this matrix K, and you check what is this value. Okay. And as we discussed, what should be the determinant of this matrix in the previous classes, global stiffness matrix without imposing any boundary conditions, what would be the determinant. You check that and then see whether you are getting that the determinant will be of this matrix will be 0. Okay. Now, once we have the global stiffness matrix, next part is to calculate the apply the boundary conditions. Now, how will you do that? If you remember, in this case, in this case, what are the things we know and what are the things we do not know? What are the unknowns are unknown degrees, unknown displacements are, this is unknown, this is unknown, this is unknown, and this 3 is unknown, and then this is known, this is known, this is known, and this is known. What we need to find out is, now we need to write the stiffness, we need to write it, and we need to write it. So, what will be the, let us write the, what will be the deformation vector? Deformation d will be, then this is d1, d2, d3, then d4, d5, d6, right, and d4, you look at our problem was like this, if you remember, and this was this is 1 2 3 4, then 5 6, and we have this was simply supported and this was roller supported. So, boundary condition is d5 is equal to d6 is equal to d4, they are all 0. So, only unknown are, this is unknown. So, this is unknown, right. So, this we can write as d unknown and d known, okay, where known is d4, d5, d6, and d unknown is d1, d2, d3, d4. Okay. Now, if you remember, we need to write then k as like this, k. Okay. Now, then what we can write is k will be and then what are the force vector? Let us write the force vector. F vector is F vector will be F1, F2, F3, F4, F5, and F6, right. And what are the forces we know in this case? we have only a vertical load in this direction, at this point we have a vertical load P, all other joints there is no load. So, the force will be F1 is 0, F2 will be minus P, and this is 0, 0, 0, 0. This is the entire force field. Okay. So, this is the displacement, this is the force field. Okay. Now, again corresponding since this the corresponding force field also we can partition like this. Okay. Now, you see if you remember we discussed the partition also. Now, point number 1, 2, 3 their displacement needs to be determined, and then point number 1, 2, 3 we need to determine the displacement. So, the matrix can be partitioned like this. Matrix can be partitioned like this. Okay. Now, this, so what will be our so matrix will be, so if we partition it, the matrix will be now what is then our force displacement relation? This is the matrix K, and then this is D1, D2, D3, this is the displacement, unknown displacement, and correspondingly it will be F1, F2 and F3, right. And what is K? K will be, if you look at there, K will be this part, K will be this part. K will be only this part. Okay. Now, how to do that? So, a final expression is that Q, general expression is F unknown is equal to F known, and F unknown is equal to K sub matrix K11, K12, or you can write KKK, KKU, and then KUK and KUU unknown, and that is equal to D unknown and D known. Okay. So, what from that what we can write is F unknown, F known is equal to KKK into D known. Here this is this same. Okay. Now, Kk is known, and then if you write it, let us write it quickly, then the matrix will be, the final matrix is something like this. Here it is half, then 0, minus 1 by 4, and then 0, 3 by 2, root 3 by 4, and then this is minus 1 by 4, root 3 by 4, and then 5 by 4. This is, and then displacements are D1, D2, D3, and unknowns are 0, minus P 0. This is the force field, and if we calculate them, then of course there will be A E by L as well. There will be A by L as well. So, then D1, D2, D3 will be, D1 will be 0.1433 P L by AE, and then D2 will be minus 0.750 P L by AE, and then D3 will be 0.2887 P L by AE. This is the final solution. This is the final solution. So, these are the displacements at various joints, and D4, D5, D6 will be 0, and this is D1, D2 and D3 are these values. So, we have already obtained what are the forces for what are the forces for what are the forces, what are the displacement, what are the displacements, okay, at various joint. Now, once we know the displacement, you see we need to find out, we need to find out the joint forces as well. The joint forces means F u we need to find out. F u we need to find out. So, what will be F u? F u will be this is the force known, joint the forces at joint known, and this force at the joint we need to determine, and then F u will be, this is the partition after partition, and from that what we can write is F u will be that k u k into du plus k u u into du. Now, dk. So, this was d unknown. Now, we have already obtained what is the value of d unknown. The value of d unknown is now this. Value of d unknown is now this is d. This is entire thing is du, and then dk is 0. Dk is 0 means because at those points your displacements are 0 because it is supported. So, F unknowns are F4, F5, F6 is equal to this into D1, D2, D3, dk is 0, this is 0, and what is this matrix? This matrix will be this one. If you look at this expression, this matrix will be this one. This matrix is this one. Now, if you substitute that, you get F4, F5, F6. What are the F4, F5, F6? F4, F5, F6 are the support reactions. So, we have already obtained displacement, support reactions, and then quickly what we need to find out is the member forces. Now, member forces, if you remember, the member forces are the member 1, the member Q1 will be the force in member 1 if, or N1 if you write, N1 is the force in member 1. This will be AE by L into minus lambda x minus lambda y, lambda x lambda y into your degrees of freedom in various joints. The member 1 is, this is the member 1, this is member 1. So, member 1 is, we have connected degrees, the joint, the displacement and two ends are d5, d6, d1, d1 and d2. So, it will be d5, d5, d6, d1 and d2. Okay. Now, lambda 1 and lambda x we have already obtained, d5, d6, d1, d1, d2 is already obtained, and these are the values for d1, d2. D1, D2 is already obtained, and these are the values, and for D5 and D6, D5 and D6 will be 0 because it is the displacement at the hinged point which is supported point, which is 0, and from there if you multiply it we will get N1. Similarly, if you get N2, N2 will be AE by L, again lambda x, lambda y, lambda x, lambda y into, now N2 is member 2. Member 2 is, this is member 2, member 2 is connected between this point and this point. So, degrees of freedom are D3, D4, D1, D2. So, it will be D3, D4, D1, D2. Again, what D3 is already calculated, D1 is already calculated, D2 is calculated, D4 is 0. So, we can substitute these values, and similarly N3 will be AE by L, and then same thing minus lambda x, lambda x and lambda x, and finally M, this is the point which is connected between this and this, it will be 5, 6, 3, 4. So, D5, D6, D3, D4. So, D3 is calculated, D4, D5, D6 they are all 0, you can calculate N3, values of N3, and if we do that, let us do it for first. Let us do it for first. For N1, N1 is AE by L, lambda 1 we have already calculated, that is half, minus half then it is minus root 3 by 2, then again half and root 3 by 2, root 3 by 2. Okay. Now, d5, d6 they will be 0, d5 and d6 they will be 0, and d1 and d2 they are, we have already calculated d1 and d2 as d1 and d2 is at. If we substitute that 0 0 and this is 0.1433 and minus 0.750 and of course, PL by AE, PL by AE, that LAE they will get cancelled each other, and these values will get minus 0.5774, which is actually minus 1 by root 3. This will be P, minus 1 by root 3 P. Okay. Minus 1 by root 3 P. And then similarly, if we do it for N2 and we can do it for N3, and we get N2 is equal to minus 1 by root 3 P, and N3 is equal to 1 by P by 2 root 3, P by 2 root 3. P by 2 root 3. Okay. Now, let us see the results. The results are, this is the results we have, right. This is compression, the compression, that is why you got minus here, and then you got minus here, that is why it is compression, this is compression, and you get this is positive. So, this is the single method. You can get the displacement, joint displacements, you can get internal forces, you can get support reactions, everything. So, this is a very small demonstration of direct stiffness method for truss, and believe me, no amount of lecture will help you will help you to understand the concept, but to make yourself comfortable with the different steps involved in this method, there is no way other than practice. So, please apply this method to some simple problem. Two things please do. You take first you take a smaller problem which have 3-4 members with the total number of joints, unknown number of unknown degrees of freedom are less, restricted to 3, so that you can get 3 or 4 and get apply all the steps the way we have applied now and get the final solution. This is the manual. You do the steps manually. Then next thing you should do, you write a code where all the steps that you are doing manually, you write a code for that, and then first thing you validate your code using a very standard benchmark problem, smaller problem, and with hand calculation and what results your code gives you, and then you take a bigger problem where your number of unknowns are more, and the final matrices final matrix that you get, that will be of larger size, which involves so many manual calculation. You do that problem using write a small computer program, and you will see and compare this method with the methods that we learned in previous weeks, like slope deflection method, moment distribution method, where maybe those methods were developed in those times where there was no computers, but that those methods required huge manual calculation, right? But these methods is not required, and it is suitable. See, at the end of the day, what is important is whether a method can be translated into a usable code or not. Okay, if a method is rigorous, sophisticated, very sound mathematical background, but it is difficult to translate them into a code which can be used very easily, then the method doesn't become that much successful. Okay, so it's a good thing about this method that it can be translated into code, and that please you try yourself and then only you can appreciate in a better way. Okay, then quickly next week what we do is we will apply direct stiffness matrix for direct stiffness, again direct stiffness method for beams, and then subsequent weeks we will see how to apply direct stiffness method for frames. Okay, then we will stop here. See you in the next class. Thank you.